I'd like to welcome everyone today from the local water utility, Icon Water, Territory Government, and academic and catchment management participants to the ARC project results presentation for optimisation of catchment management with stable isotope studies of water storage and yield in our Cotter catchment. Firstly, I'd like to acknowledge that this meeting is being held on the traditional lands of the Ngunnawal people and pay my respect to elders past, present and emerging. In being curious, sharing and learning about our local waterways today, we are caring for our country and people.
So Alex is a PhD candidate specialising in the storage discharge dynamics of the Upper Cotter catchment in the ACT, which is precisely what we're meeting about today. He spent the last 3 years trudging his way down to Canberra and collecting water samples from the catchment to understand, the time it takes for water to travel through the catchment from rainfall and precipitation right through to streamflow. Prior to starting his PhD, Alexander completed a Bachelor of Environmental Systems with honours, and his other interests include data science, open data, open source software and agriculture. So thank you, Alex, for presenting to us today. Willem is the Associate Professor of Hydrology and Catchment Management at the University of Sydney, and he's their leading hydrologist. His main research focus is the development of sustainable water management in relation to varying climate, particularly improving quantitative tools to improve management and policy decisions. Well, that's what we're here presenting on today. Willem works across several projects with industry across Southeast Asia and South America. And he's supervised more than 15 PhD students and 20 honours students during his career at the Uni of Sydney. So thank you for presenting to us today as well, Willem. The results presented today are, just so people are aware, are just one component of the broader ARC linkage project agreed by Icon Water, which was then Actu Corporation, and the University of Sydney in 2012. You may have seen from the attached proposal that the research objective is focusing on how water reaches the streams and dams to help identify where land and water managers might better focus our efforts to increase yield. The interest in today's presentation highlights the breadth of people involved in our water and land management in the Cotter. As I said before, with attendees including water utility and security modellers and engineers, ACT Parks and Conservation Service rangers, water policy scientists from ACT Government, and also local leading water science academics locally here in Canberra as well. So just to repeat the housekeeping before I hand over to Alex and Willem. One, can everyone please make sure their microphone's muted and that they stop sharing their video to make sure we preserve our bandwidth for the presentation. Questions will be addressed after the presentation, and you're welcome to type them into the chat throughout to allow them to be captured. Or at the end, when I ask for questions, you can put your video on to indicate that you're wanting to ask a question, and I'll go to you based on the results that Alex and Willem present. So now, Alex and Willem, over to you guys. Thank you.
All right. So, just to highlight where we came from, this is we're presenting part of this ARC linkage grant that we had with Icon Water and Actu before that. And particularly, you just want to highlight there was particularly a big vegetation component and a hydrology component. And today we're mainly talking about the hydrology component. And yeah, just like Ben said, I also want to recognise, of course, the people from the Gadigal Nation here at the Eora Nation here at Sydney, which we wouldn't want to ignore, whose ancestral lands we are currently sitting on, and so that is also part of our recognition to those people. Anyway, so just to give you an overview of the ARC linkage project in the Cotter that we've been working on. So there was an original project in 2010 that ran to about 2014 that started off, and that was mainly focused on vegetation and mainly focused on eucalypt transpiration and particularly nighttime transpiration. And that fed into this new project. However, it took quite a long time to kick this project off, basically because there was quite some long time needed for the contract negotiations. And after that, of course, we had to, before we could start doing the drilling, as I have a picture from, we have to adhere to all the, of course, ACT government regulations in terms of, and because we were working in the Magic National Park, to be able to get through to all that and make sure that we're actually showing that we are doing a careful job of putting those piezometers in. And so I also took me a little bit of time to actually attract a PhD student until I found Alex. And so Alex really just started with his honours in 2016 and his PhD in 2017. So again, there's two components. We're reporting on the hydrology components, which Alex is finishing off hopefully later this year. And Mark Adams, Tom Buckley, and his co-workers have been working on the vegetation component. I know they've written several papers in that area, which you can find on any of the databases. And I also know that they lost all their infrastructure in the last bushfire, because we actually saw it there, and they're still on the process of cleaning that up and getting it out of the park. So yeah, I'm afraid that quite a bit of data on the last bit of the research is lost. All right, I'll pass the microphone to Alex, and then you should go to...
It is that one? All right, cool. All right, good morning, everyone. All right, so I'll just give you a background into the hydrology component. So a lot of prior research has indicated that vegetation and storage play important roles in water yield. However, the exact hydrological processes are poorly understood. So what water is vegetation using? So from what part of the soil zone are they accessing? Shallow soil water? Are they accessing deep groundwater when they need to? What are the main water storages? Is it groundwater? Is it water held up by vegetation? Is it water travelling through fractured rock aquifers that might be in the catchment? And it's kind of poorly understood how these sort of features affect stream flow. If we have a poor understanding of how these hydrological processes, if we have a poor understanding of them, then we limit our ability to effectively protect and manage catchments. In Australia, this is particularly crucial because we obviously face challenges with water security now into the future. We've got an intensifying climate, we've got longer droughts occurring, obviously got increased bushfire risk, and all these factors affect water yield coming from our forested catchments. So there's a clear need to improve how catchments function. And keep going. So the aims of the hydrology component of this project was to understand the storage streamflow dynamics in the Upper Cotter. So we're particularly interested in understanding fundamentally how streamflow is generated. So what are the main flow pathways? For example, is it quick runoff? Is it groundwater, slow moving groundwater through the catchment? And particularly we're interested in how long does water reside in the catchment. So how long is it taking from precipitation through to streamflow for water to move through? So if we have an understanding of how these processes generate streamflow, it can give a guidance on drought resiliency of the catchment, and it can aid catchment management by prioritising the main impacts on the main hydrological processes. So just in case we're all familiar with this is a diagram ripped from Icon Water's website, just overviewing the water supply for the ACT. And so the Upper Cotter is this region up here. So we were interested in we were doing research in the area above the Corin, above Corin Reservoir, and our particular cutoff was the Gingera gauge here. So this area, the Greater Cotter catchment and the Corin's an important area for the ACT. It's obviously the primary water supply for Canberra. It's a national park, so it's a well-preserved alpine environment. It's a biodiversity hotspot there. It's also important for the people of Canberra for recreation as well. As I mentioned, the Corin catchment, which I'll refer to as the area draining to Corin Dam at Gingera gauge, and essentially it's just the headwaters of the Cotter River catchment. It's an ideal research location because there's no dams impeding flow before that gauge, so it gives us a nice natural research benchmark catchment, essentially. To give everyone understanding the sort of the environment, that's up there. It's an alpine environment, so you've got quite large, and mountainous environment too, so quite large changes in elevation. So on the western and eastern ridges, it's getting up to 1,900 metres and then down to 900 metres in the valley. It's quite diverse in terms of geology there. So it's quite old as well. So a lot of the sediments down in the valleys date back to the Ordovician, which, if you don't know your geological time periods, it's quite a long time ago, about 440 million years ago. And on the eastern western ridges, we've got some of these sort of granitic rocks that form our regoliths here. So you've got essentially different granitoids there. So if we keep moving, the Cotter River, as it travels from south to north, essentially follows this fault, which is essentially developed as it follows a narrow band of soft rock here, where the fault lies, and that's essentially created the Cotter River as it travels from south to north. So there's been some hydrogeological surveys done of the area, and this is the one for what's called the Piccadilly hydrogeological landscape. So what I just wanted to highlight here is, so this is sort of a cross-section running from west to east of this hydrogeological region. So it gives you an idea of how stream flow might be generated here. So we've got some weathered soil layer on the top of the regolith here, and essentially water is travelling down the western eastern slopes and towards the reservoir. As you can see here, we've got quite a deep rock layer, so it's highly likely that there's fractures in these rocks where you would have slow-moving groundwater that moves towards the stream. Just to give you an idea of sort of the water balance of the area, so getting around 966 millimetres of precipitation annually, that's the average, but you can see that there's quite a lot of variability there. In terms of the removals of water from the catchment, you can see ET dominates. So when I say ET, I mean evapotranspiration, which is essentially losses to evaporation and transpiration by vegetation in the catchment. So evapotranspiration dominates the water balance here, so about 700 millimetres a year lost to ET, so it's an important controller. In stream flows average about 283 millimetres a year, but again, quite a large variability. The figure here just highlights that there's a large interannual trend. So you can see ETs will be highest in the summer, evapotranspiration is highest in the warmer seasons, as you would expect. So the red dots are evapotranspiration, the average evapotranspiration for each month. The columns are precipitation, and the blue line's stream flow. So you can see there's a slight spring dominance on average to precipitation, and so stream flows are also highest in this season. You can see stream flows only really seem to kick off once ET subsides in the winter as well.
Message received today.
Oop. Keep going. So to give you an idea of our sampling design, when we installed the piezometers was in February 2016, after Willem said everything was sorted with the contract. So we put some loggers in wells, which I'll show the distribution of in a moment. And so those loggers were recording depth to water and temperature every 2 hours, although we do have some periods where the loggers were recording every 15 minutes. We did regular sampling in the catchment, so we were doing going up there on a monthly to quarterly schedule, and we would take water samples from each site. And this, and we highlight, as far as we know, these are the first observations of groundwater in the Corin catchment. So it might be of interest to some of you what this data might show. And we also did a sampling campaign. So from September 2018 to April 2019, there was 2 auto samplers installed, one collecting stream flow at Gingera gauge and one doing daily auto samples of rainfall collected near Cotter Hut in the catchment valley. And then we set these up to collect weekly auto samples from 2019 to April 2019 to March 2020. We had a couple of setbacks with the equipment over this period, including losing quite some infrastructure to the bushfire as well, but we weren't nearly as affected as the vegetation component. So overall, there's 21 independent sampling trips in total over this period. So this is the distribution of sampling points within the catchment. So sorry for our confusing naming scheme, but essentially this is the Canberra gauge up here. And this is where Cotter Hut is for sort of reference for people who are familiar. So we've essentially got some groundwater wells distributed in some of the higher slopes, lower slopes, and by the river. And also distributed towards the southern end of the catchment as well. We took some surface water samples to cover sort of a range of different streams in the catchment, some that would be sort of direct runoff over the higher, more elevated areas. And also we have different collected samples along the main stream to sort of see how the ions and the water quality evolves towards the northern end of the catchment. Okay. So these are the observations we took in the field. So we took standing water level. So when we're actually doing our field trips, we took a manual reading of the water levels in each of the wells. We took temperature of the water in the wells and the streams. We took pH, electrical conductivity, so both specific conductivity and just regular electrical conductivity. We did field alkalinity as well, so we were doing titrations to determine the amount of calcium carbonate equivalent. In the labs, we analysed the water for stable isotope values, so your values of oxygen, 18, and deuterium. And we also did the major anions, major cations in the water. So this is the hydrology of the study period. So the study period, we're saying from 2016 to 2020, so once we had instrumentation and started sampling in the catchment. So you can see here, stream flow in the winter of 2016 was particularly high. This coincided with a particularly wet winter across the southeast of Australia. And after that, stream flows decayed and it's really dominated as a base flow period, aside from these occasional storm events in December of each year. Here we've got actual ET, so it sort of fluctuates according to season, and it's quite a steady signal with quite low variability as well. And down the bottom, we've got change in storage. Now, this isn't the change in storage in terms of the dam, but this is in terms of the change in storage in terms of the water balance. And this is determined by taking the cumulative sum of precipitation and subtracting the cumulative sum of stream flow and the actual evapotranspiration. Some key things to point out here is that the storage has been decaying. Essentially, the change in storage within the catchment has been decaying since this wet winter in 2016. And it sort of really hit rock bottom just immediately before the fire here. And then you can see after the fire occurred in January and February of this year, you can see that we've had a stream flow peak and we've also had a detectable drop in actual evapotranspiration as well. You can see here that the amount of that's moved in or theoretically moved into storage is increased from this event as well. So this is an overview of the standing water level in the piezo's that we've installed across the catchment. So hopefully you can read it. So just to highlight that these wells are installed to different depths. So essentially the wells were installed till we hit groundwater or till we hit rock, or to a maximum depth of 12 metres. That was the amount we could maximum depth we could go down to. Sorry? Oh, yeah, sorry about the labels missing the last two, but that's groundwater 7 and groundwater 9. Essentially, I don't want to dwell on this too long, but if you're interested in this data, this is something we can share, but I just want to highlight in some of these deeper groundwater areas, you can see that the groundwater is also following this decaying trend or decreasing trend, I should say. And in some areas after the wet area, you can see that groundwater is dropped below where we can sort of get depth. Yeah, so groundwater 5 is in this sort of elevated here towards Licking Hole Creek, if you're familiar with that is. So that's where Licking Hole Gauge is, so it's north of there. So it's on the eastern side of the catchment. So you can see there the standing water levels drop below 12 metres. Yeah. So we'll move on, but if you're also interested in this, bring this up at the end, we can discuss this more. So this is sort of a summary of the pH of water in the catchment. So you can see here that the pH of the groundwater tends to be quite acidic, so averaging about 6 pH for these sort of deeper wells. Groundwater 4 here is located here, and this is located in a swamp. So you can see here that the pH here is a lot more neutral. It doesn't sort of, it's not located on an area where it's got these highly weathered sandy soil profiles there. And it's rather, there's a bit of accumulated organic matter, which is, yeah. And you can see the pH of the surface water is a lot more neutral. Aside for 5, which is up here. By the way, you can see here that the pH of the surface water, interesting, is a lot more neutral than the groundwater, indicating possibly that, what was I going to say? Oh yeah, so we're thinking that, so once the surface water is flowing, it could indicate that it's becoming more enriched in, I guess, oxygen, and then, so it's under less reduced conditions. So keep going. Electrical conductivity, you can see here, no surprises here. The EC is particularly low across the catchment. We also have the ion balance for what is an average ion balance for all these sites, but it's at the end if you'd like to see it. But essentially here there was nothing particularly interesting. All the ion concentrations are low as indicated by the electrical conductivity. Yeah, so it's particularly fresh water. Yeah, so the alkalinity, however, was interesting. So the calcium carbonate equivalent, that was the dominant anion in the catchment. So indicating there are some carbonates distributed across the catchment. Again, relatively even distribution spatially as well. So there was some slightly higher carbonates in this creek running towards the Cotter River along here, but again, nothing substantial. So the stable isotopes are quite interesting. So as a background for those who aren't familiar, there's in water, you've got, as we all know, water is H2O, but then the hydrogen and the oxygen components of that water may contain a stable isotope of water. So these certain ratios of water, so you'll have heavier isotopes, so oxygen, 18, and deuterium, and they sort of behave in predictable ways, and we can understand, we can use them as useful traces. So with rainfall, there's a seasonal pattern of the distribution of the stable isotopes in rainfall. So the blue dots are precipitation, as rain here. The green dots are surface water, and the red dots are groundwater. So you can see here the more enriched values, so higher contents of oxygen 18 and deuterium occur in summer rainfall, typically, and then winter rainfall tends to have a more depleted content of deuterium and oxygen 18. Other effects can also influence the content, so heavier rainfall events also tend to be more depleted, but the overall dominant signal is sort of the seasonal signal in rainfall. An important thing to note here is that the groundwater and the surface water tend to have, they're quite close in terms of their oxygen, the stable isotope content, and it sort of matches a more depleted rainfall signal that would corresponds to more depleted winter rainfall events. So this is a first indication that the streamflow and the groundwater has its origins in the cooler season rainfall. Oh, sorry. So the lines here, this is the global meteoric water line. So that's the sort of, I guess, the average ratios of the oxygen-18 in deuterium for rainfall in oceans across the world. And this dashed line here is the local meteoric water line, which is the standard, so the ratios you would expect in the Cotter catchment. So you can see here it's pushed off the global meteoric water line, and that's to do with factors such as distance to the coast, the temperature of the region, and where the water's coming from, the origin of the evaporation as well. Keep going. So this is some of the auto-sample data here. So when we were collecting the daily samples between October 2018 and April 2019. So you can see here we've got precipitation on the top, streamflow in the middle, and the oxygen-18 values of rainfall, P, and streamflow is SW here. Just I'll point out initially that there was a couple of setbacks here. The auto-sample stopped working here, and the streamflow one, and then the rainfall auto-sample stopped working here, so this is why all the rainfall events are the same value here. So the important things to point out here are that you can see there's quite a variety of oxygen-18 values in the rainfall, and the streamflow is quite constant. We were lucky enough to collect samples during a storm event here, but you can see that the streamflow content barely budges. So if we take a closer look at that, if we zoom in on the oxygen-18 values here, you can see that the fluctuations in the stream content sort of match the fluctuations in streamflow quite closely. So if we take a close look at this storm event that occurred in December 2018, there was 87 millimetres of precipitation over 2 days on the 13th and the 14th of December, I believe. And this generated a peak discharge rate, peak streamflow rate, sorry, of 2.24 millimetres per day. And this is in the top 5 percentile flows in the catchment. If we do a simple mixing model, so when you use a mixing model, you use the, essentially you got your two M members, you got the concentration of oxygen-18 before the event, and then you've got your values during the event. What you can sort of work out is how much of this streamflow here in this event is due to the incoming precipitation. And a simple mixing model suggests a new water fraction of 40%. So what this is saying is that the other 60% of streamflow generated is water that was already stored in the catchment. It's being pushed through. So now this could be water that's in sitting in groundwater that's pushed through sort of like a piston flow model. As water comes into the catchment, it pushes out old water that's sitting there. But you can imagine with this amount of rainfall, you would be saturating some of the areas, leading to quick surface runoff as well. So this is potentially where the extra 40% comes from, or the contributions here. The other event to take note of is here is, it's only a small event, but you can see how there's a large change in the stream isotope content here. And this is essentially in March of 2019, when the stream flows were getting extremely low, and only a small rainfall event, or only 30 millimetres, can cause a large deviation in the stream isotope content as well. If we keep going, so we can do more sophisticated things with this data. So there's a global push to understand how water is transported within catchments. So if you think about your typical hydrological model, they're looking at pressure propagation rather than mass transfer. So what they're looking at is just what is coming in, what is coming out, but they don't really tell you how long water is taking to move within the catchment. So we can use this stable isotope data to help constrain water transport models. The particular model I used in my research was the storage selection model or framework. And what it does is it tracks rainfall events in storage until they exit via streamflow or evapotranspiration. So with the model parameters, you constrain their behaviour with the stable isotope data, because essentially the stable isotope data, it's tracing the water through the catchment. So you associate particular rainfall events in storage with that stable isotope content. And what you try to do is you try to reproduce the values in the stream with what's available in storage and what you know the different fluxes are of streamflow and evapotranspiration. So essentially based on the input and output signals, you can estimate the residence and travel times of water within the catchment. So this is an overview of the framework, the storage selection framework. So as a high-level overview, so you can think about your typical hydrological hill slope as like this. So you've got evapotranspiration exiting through here, streamflow down here. And as you've got rainfall entering storage, you can imagine storage on the bottom. That's going to be typically your older water that's recharged and sitting there. And water exiting through streamflow is going to be made of a variety of different storages here. So you've got your surface layers that might even have quick flow paths to the stream. But you can imagine streamflow is going to be sort of an aggregate of water of a variety of ages in the catchment. Now with evapotranspiration, it's going to be, vegetation, they're going to be accessing water that's essentially going to be the least energy to use. So you can imagine they may have a preference for water in the upper root zone. But we also know that eucalypts tend to access deeper groundwater when they need to in times of drought. Essentially what these plots are here is sort of the distribution of water ages in storage. That's this plot here. The distribution of water ages in evapotranspiration that they might prefer, and also the distribution of water ages in streamflow. So what is this just to highlight is theoretically you can imagine that evapotranspiration might have a preference for the younger water. Streamflow might have a preference for water of a variety of ages, and the storages reflect these sort of preferences here. So the data set we use with this model, it's a combination of, so we've got our precipitation here this is from the Cotter Hut rain gauge. This is streamflow from Canberra gauge. And so what I did was that with our daily isotope data here and our observations of the stream isotope data over time, I combined that data with some observations of stable isotopes and rainfall from Tumbarumba, so just Harrywood Caves, just to the west of the Corin catchment, and then combine that with some model data where we tried to model the daily values of oxygen 18 and rainfall using a mixture of weather and back trajectory data. So this plot here is the model. It's an ensemble of simulations trying to simulate the value of oxygen 18 in the stream. Essentially, we were able to reasonably match the sort of the baseflow signal of oxygen 18 values in the stream. And to successfully reproduce this, the oxygen 18 values, we need to assume that vegetation had a very strong preference for younger water. So it was clear that vegetation was seeking recent precipitation events to successfully reproduce oxygen 18. Streamflow had a mixed preference, so it seems that streamflow had a combination of older and younger water in the catchment. And then also the size of the active storage can impact sort of the reproduction here. So, what the model estimates that there's about 2 meters of is the size of the active storage, and what that means is that's sort of the detectable storage that will lead to contributions of stream flow and vegetation. So it's approximately around that size. So here, this is the mean travel times of the different fluxes and storage. So you can see here that constraining the model with stable isotopes, you can see that evapotranspiration tends to access water that's quite a lot younger. So that could be water that's anywhere in the 1 to 2 year range. That's what it prefers, or to simulate the oxygenating values. But you can see stream flow here in storage here that the water residing in the catchments around the order of several years for about 3 to 9 years. That's the average age of water in stream flow. And you can see here the distribution of ages in storage is quite bit wider. One thing I should mention here is that these travel times are calculated, they're adjusted by the size of the fluxes. So, for example, the stream flow is adjusted by the flow rate. Same with evapotranspiration, it's amount weighted, and storage is also weighted by the amount that's in storage as well. So what do these results mean? So you can see here some reasonably long travel times suggest some continuity of flows. So it suggests that there's a drought buffer inherent within the catchment. And you can think about it this way, it's a positive for ecology, particularly for the stream ecology. So you can imagine if there's a particularly long drought, you still may be able to expect water is travelling through the catchment. Are they long enough, however? Well, these are the average sort of transit times. So you can imagine if there's a particularly long drought and a particularly severe drought, such as the Millennium Drought, you can imagine that these flow rates or these travel times may not be long enough yet. They indicate that there's some long subsurface flow pathways within the catchment, and that supports the idea of the hydrogeological landscapes with the estimates they sort of provided that the residence times of water sitting in the aquifers is in the range of years. If we think about vegetation preferring younger water from the recent precipitation, it sort of indicates that evapotranspiration is a strong controller of stream flow. And you really need these particularly heavy precipitation events to generate recharge. Now, this can be concerning with the shifting seasonal patterns of rainfall that have been observed in the southeast of Australia, where we're seeing less winter dominance in rainfall, and it's sort of shifting towards summer. Now, you can imagine that if rainfalls are shifting towards summer, where the fluxes of rainfall are higher, the evapotranspiration rates are higher, and it's going to be rapidly seeking recent precipitation. This would also indicate there's going to be less recharge into groundwater and perhaps into streams and then aquifers as well. So we're going to keep building on this. So we have an understanding of the average catchment conditions. So our travel times are sort of what the sort of average conditions were over the study period there. And what we also implemented was only a static preference. So we assumed that water in vegetation would have the same preference throughout the study period, and then the same for stream flow as well. But you can imagine that they might have dynamically changing preferences based on the prevailing weather conditions. So if it's particularly wet, you imagine that stream flow might be made up of water from a variety of ages, or there might be more younger water entering the stream flow, as indicated from the mixing model. So that's one area you're going to look at by better parameterizing the model to sort of have these changing preferences in time. One exciting thing we've got coming as well is that we've got some samples that are going to be analysed by ANSTO, the Australian Nuclear Science and Technology Organisation. So they're analysing 5 surface water samples collected from near the stream gauge and 3 groundwater samples analysed for tritium. We only got 8 samples. I put in for more, so we'll see if we get any more coming. Tritium is useful because it's radioactive essentially, and so it decays over time. So the amounts of tritium in rainfall has changed over time. It's quite stable now, but you can estimate based on the previous inputs of tritium into the catchment and the current ones, based on the amount of tritium in the stream, you can kind of date where that water has come from as it's decaying. So if you have very low tritium contents in the stream flow, it would indicate that the water is quite old. And some other studies around Southeast Australia, so in, what's it called, down near Melbourne, the Otway Ranges, they found that water could range from years to several decades old. So they found even some of those very low stream flows that water could be 30 to 40 to 50 years old in those stream flows, or what they estimated, indicating that, so there is these large contributions, or there is a contribution of these very, very slow pathways through the rocky areas of the catchment. And just as a disclaimer, as well, stable isotopes often underestimate the travel times. However, they can be used to sort of provide an average indication of what the travel times are within the catchment. But that's some exciting stuff coming. One thing we wanted to highlight is that some of this research is under review at the moment. So in particular, some exciting things to point out is that it's the first time this storage selection model has been applied in Australia, and it's rarely applied in dry environments. So this is dry relative to the rest of the world, even though the Corin's pretty wet for an alpine Australian environment. And the results highlighted some unique preferences to the Australian eucalypt forest. So that's underway. So we do have some further research questions from the outcomes of this study. So we probably need a more sophisticated implementation of how evapotranspiration selects water to help constrain the model further. If you have a better idea of how evapotranspiration selects water from the catchment, from catchment storage, because it's the larger flux and essentially it looks like it's controlling stream flow, if you have a better handle on how evapotranspiration works, it helps with stream flow and storage behaviour. We're also curious about the role of the marshes, peats and swamps in the catchment. So these features appear on the key drainage lines and most likely slowing water down the landscape. And so we're also interested in what are the contributions of sort of groundwater or deep flow paths versus the slow water moving through the swamps and marshes to base flow. And the tritium will help highlight this as well to a degree. We're also interested in the fire recovery of these features because we went into the catchment in March to sort of see how our equipment fared. And one observation is that all the areas that were previously had swamps on them, you could see water pooling there on top of the surface. So it was obvious that there were key stores of water in the catchment as well. As you also know, I noted on average there was a spring stream flow peak, so which normally suggests stream flow from snowmelt. So we'd also like to see a further question if you should be looking at snow in the upper elevations, quantifying snowpacks and seeing how they contribute to stream flow as well. This is something that could be investigated with stable isotopes as well because snow tends to be very depleted and has a unique signature. Just to highlight some of the other analysis and work that's ongoing. So we've got some, a lot of the IAM data was only received or finished, the analysis was only finalised recently. So we're looking at the spatial relationships of the ion balance in conjunction with the stable isotope data to sort of understand the spatial partitioning of water and seeing how the relationships to groundwater and stream flow spatially across the catchment. And there's also some more fundamental modelling work going on. So essentially storage is the most elusive part of the water balance, and so I'd like to get a better handle on the size of the storage and what that sort of means to stream flow. And this is being investigated using a variety of methods, so stream flow recession, using combination of conceptual and distributed models to look at the distribution of water within the catchment, and sort of just looking at the water balance over time to sort of examine the delta storage and see what that can inform along with these two other methods. And sort of having, knowing the size of the storage will help model stream flow and evapotranspiration and help our understanding of how these processes essentially and what the origins of water are. So the data from this study, so the data I mentioned here, we intend to make it public available. So we have built up quite a comprehensive data set of field and lab observations. And this data is part of the manuscript that's in preparation, so it'll be combined. And we intend, once this manuscript's released, then the data will become available at that time, should everything be fine contractually, which I think it should be. We're also interested in any other or further data that's collected from the catchment. So if anyone has any data they think that could be help in this sort of work, we're interested in it. I mean, if anyone has an urgent need for any of the data we've discussed here, we can also look at supplying that now as well. So just some acknowledgements. So ACT parks have always been helpful when we've wanted to access the Upper Cotter, always been friendly, letting us use the Cotter hut, which is always nice of them, and then I'd just like to thank them. Icon Water and the Australian Research Council for providing some funds to do this research through this linkage grant, so we'd like to thank them as well. And I'd also like to acknowledge the Australian Government Research Training Program for providing me with a stipend to do this research as well. Just a small bonus here. So we all know that unfortunately, the upper catchment has burnt recently. So you can see this is before the fire in January 2020. You can see afterwards, particularly severe. I think nearly all the catchment's been burnt, which we also saw when we were up there in March. But as a small positive, it's been cloudy ever since March, so it's hard to get a good satellite photo, but you can see there are patches of green coming back. And as with the 2003 fire, these things always recover, but it was distressing entering the catchment then. But yeah, it's a small glimmer of hope there. Anyway, thanks for listening to me rant for half an hour, I think it's been. But yeah, happy to take questions. I can see some questions are coming through as well.
Alex, firstly, thank you to you and William for presenting to us a really great use of data alongside a story of I guess, another way of seeing the raindrop coming through the catchment, and really appreciate hearing from you and your perspectives on this. So I will open it out to other questions, and I do see that Jason, you put one on there in chat. I'll come to that in a second.